Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the fun things happening inside the universe. I love being a theoretical physicist. I love being a cosmologist. I get to work on some of the coolest topics in the universe and try to figure out what's going on out there. And it's a really fun thing to do. Hey, Jasmine, great to see you in for us today. Really, really nice to see you. Are we going to find out what dark matter is today, Paul? Good question. And hello, Paul. Welcome, as always. It would be great, right, if I could start a stream like so. We figured out dark matter. Not yet, I'm afraid. I don't have any major updates in terms of dark matter. We haven't discovered it. We haven't suddenly figured out what it is, but we're working on it, and we're going to get to that today. So, hey, David Dunn, great to see you as well. How am I doing? How is Finland? Well, thank you for asking. I am doing well. Finland is amazing. I absolutely love Finland. It's my favorite country. Helsinki is a great city to live in. The group here is amazing. The people are great once you get to know them. Bit standoffish, but great people. So I'm happy in Finland that I am doing overall well, despite everything going on, like grants writing, which is grants writing is the thing I'm doing these days. Pretty much the only thing I'm doing these days. But apart from that, I am doing well. You are not late, Scott. Don't worry. 2 minutes is perfectly acceptable. You can always add on an academic 5 minutes and then come in whenever you want. So don't worry about that. But great to see you here, Scott, as well. I have a box of dark matter with me. Well, maybe I do. There probably is dark matter all around me. Like, is dark matter in the room with you now? Actually, probably yes, it is. But anyway, back to I was in the middle of the introduction and already went off on tangents. Hey James, great to see you. Great to have you here as always. Seeing all of the regulars tuning in. Always great to see people. So yeah, I love being a theoretical physicist. I love getting to study the universe, and I really enjoy jumping on YouTube, Twitter, wherever you're watching me from, and just chatting about all of the cool things I get to study. I study some really cool things: dark matter, gravitational waves, the CMB, the cosmic microwave background radiation, bunch of stuff. And I think it's an important part of a scientist's job to communicate our science with the general public. After all, most of us are partly or entirely funded by public money. So I think we should share our knowledge with people. And I think doing science communication, talking to all of you about my science, about my research, has made me a better scientist. And I think more people should do this. So, bringing it back, welcome to Cup of Cosmology. This is the place where you can ask any questions you have about the universe, about cosmology, about dark matter, about gravitational waves, anything you want to know. If you like Cup of Cosmology, if it's your first time here, welcome. If you're a return viewer, great to have you as well. Please do subscribe to the YouTube channel if you haven't done so already. Like the broadcast, leave a comment down below, click the notification bell, all of the usual YouTube things to help me increase engagement. I can tell you it is working. Over the last month, my viewership has increased a lot on YouTube. I'm really happy with that. So thank you to everyone who's been liking, sharing, boosting the engagement. I do appreciate it. If you're watching over on Twitter, it's great to have all of you Twitter followers here as well. If you want to join the conversation, you do want to head over to YouTube. Easy to find. It's youtube.com/c/cupofcosmology, and then you can click on the live video. Or if you're on my Twitter feed, you can go to the second tweet below the stream that you're watching, and there you can find the link to join me over on YouTube. Figuring out my introduction now, it's almost becoming seamless. So, as I was saying, I like jumping on jumping on whichever platform you're watching on and chatting about all of the cool things I get to study. Some weeks we don't have topics, some weeks we do, some weeks I have guests. I have a couple of guests lined up. I have 2 confirmed guests in October that I'm really looking forward to, and potentially a third. So going to get some more guests coming in a few weeks, which is always fun because then I get to learn new things as well. And then I don't spend an hour talking by myself. So it's always nice to have a guest in. And today we do have a topic. Today I'm going to talk about dark matter. So am I hyper today? If I'm talking too fast, please do let me know. If not, don't worry, I'll just continue speaking fast. The good thing about being on YouTube is you can slow me down in the replay. So, big question first. What is dark matter? This is obviously where we need to start. So as always, feel free to ask me any questions. If it's about what I'm talking about or off topic, just put your questions in the chat. If they're off topic, I might not answer them as quickly, or I might leave them for a future conversation. But just anything that's on your mind that you want to ask me, please feel free to leave your questions on the YouTube comments, and I will do my best to try to answer all of your questions. So, first big question we have to answer today is, what is dark matter? And as I already said, we have no idea. But let's rewind that slightly. So, we know that the universe has three main components. Everything we see, everything we're accustomed to, everything from me to my tea mug to the stars we see in the night sky, all of this is normal matter. And normal matter only accounts for 5% of the energy content of the observable universe. Only 5%. We are the 5%. There's another overwhelming 25%, which is in the form of dark matter. So dark matter is this type of matter that interacts via the gravitational force, but doesn't interact via any other force as far as we know. Maybe it has weak interactions, probably doesn't have strong interactions, definitely doesn't interact via the electromagnetic force. Hey, Alison, great to see you. Don't think I've seen you in here before, maybe once. Great to see you in here, Alison. Always good to see people from the shared server in here. But yeah, dark matter interacts via the gravitational force, doesn't interact via the electromagnetic force. So this means that dark matter is invisible, which is always fun, because how do we study something that's invisible? And that's going to be one of the main topics today. So 5% normal matter, 25% dark matter, and the remaining 70% is in the form of dark energy. So dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It's pushing everything outwards, and that's pretty much everything we know about dark energy. We know a couple more things, but pretty much that's everything we know about dark energy. But one of the things I've worked on the most during my career, I make that sound like a long career. I'm 3 years out of my PhD. But during my PhD and my first postdoc, and I'm still a bit ongoing now in my second postdoc, one thing that I always come back to is dark matter. And as I just said, dark matter is invisible. So then we have the really big questions, several big questions. How do we know that dark matter is there if we can't see it? How do we study it if we can't see it? Basically, what do we do with something that is invisible? And why do we think that dark matter is there, given that it's invisible? And I realized I ignored a comment from Scott. You ended up trying to explain Schrodinger's cat and quantum wave function. They are difficult topics to explain, Scott. They are not easy. If you want to learn more about quantum physics, about quantum entanglement, about Schrodinger's cat, about fun things like that, we actually covered that on the stream. I would say recently. The stream was actually recorded last November, but I uploaded it to the YouTube channel 2 weeks ago. So if you go back to videos on the YouTube channel, Cup of Cosmology YouTube channel, you should find a stream called Quantum Entanglement, where we spent a whole hour talking, me and a colleague in Helsinki spent a whole hour talking about quantum physics, quantum entanglement, and all the fun things there. And I'm pretty sure we covered Schrodinger's cat as well. Does whether dark energy is part of the pie chart of what's in the universe depend on which theory ends up being true about it? Depending whether it's a thing or just a form of gravity? That is a great question, Paul. So usually we have this nice pie chart of the components of the universe, and we show dark energy, dark matter, and normal matter. And we have a lot of reasons to believe that this pie chart is a pretty accurate depiction of what we've been able to measure till now. Now, not everyone believes in dark energy or in dark matter. There are alternative ideas. One possible alternative idea is modified gravity. Now, in modified gravity, you modify Einstein's general relativity to try to explain the effects of either dark energy or dark matter. And if modified gravity is correct, and actually we don't have a new species that is dark energy, but rather it's just an effect of space-time, then the pie chart would no longer be accurate, because that pie chart where you see like 5%, 25%, 70%, that is like the components of the universe, and that assumes general relativity. Because as far as we've been able to measure so far, general relativity is the best description we have of gravity in the universe. We haven't yet found a theory or a model that can explain things better than general relativity. If at some point we find a theory of modified gravity that does away with the need for dark energy, then that pie chart would no longer be accurate, because we could no longer say, okay, assuming general relativity, these are the components of the universe. What we would then do is, assuming this new model of modified gravity, this is the updated pie chart of the universe. I have no idea what that updated pie chart would look like. Depends if you still have dark matter in this modified gravity model or not. So that is a very, very good question. And yeah, basically it would change. So the answer is yes, it would change. That's the short version. Question from James: is there anything else in the universe that does not interact like dark matter? That is a very, very, very nice question. And that actually allows me to go to the standard model of particle physics, which is something I did want to cover at some point. And I am trying to get my standard model of particle physics, but I have slides that I use for all of my images, because for some reason I can't upload individual images. And I was on slide 1, which is the start one that you see at the beginning. And the slide I want now is slide 24, and I have to press all the buttons to get it there. But standard model of particle physics, this is a great question, James, and I'm going to answer this. So the standard model of particle physics gives us all of the known building blocks of the 5% that makes up normal matter. So all of normal matter is made up of these 17 building blocks that you see on the screen. So we have two main families. We have the fermions on the left, and we have the bosons in red. The fermions are the ones that are kind of more the building blocks, and the red ones, the bosons, are the ones that tell us how these pieces fit together. They tell us how these other particles can talk to each other. The fermions are divided into two families. We have the quarks at the top and the leptons at the bottom. Key thing about quarks is they cannot be found alone. You always find 2, 3, 4, 5, 6 quarks, but you can never say, hey, look, I've got a quark. It doesn't work like that. There's always at least 2 of them because of the strong force. Then we have the leptons. The leptons can be found in isolation. There are 3 families of leptons. There are the electron, the muon, and the tau, and each family has a neutrino. So we have an electron neutrino, a muon neutrino, and a tau neutrino. This is the bottom row here. Now, the reason I'm bringing this up, I know there's a lot of information here. Don't worry, you're not going to be quizzed on this. This is just a quick primer on what the standard model of particle physics is. Is anyone bothered by how including the Higgs boson ruined the 4x4 symmetry? Yeah, I mean, technically, the W boson already has two like species. You have the W plus and the W minus. It's just put together because one is plus, one is minus. But yeah, the Higgs boson is just kind of this thing that we added on that we need to explain how everything else gets mass. But it does kind of break the symmetry, doesn't it? Funnily enough, when the Higgs turns on, you do actually break the symmetry in the universe. So that's fun. Fun fact: Higgs actually breaks symmetry in many ways. It's a little physicist joke for you there. Hey, Jans, great to see you. Thanks for joining. Always nice to have you in the comments as well. So, is there anything else in the universe that does not interact like dark matter? This is why I just flashed the standard model of particle physics. So, there are 4 forces that we know of in the universe. There is a gravitational force. I drop a pen, it falls down. We stay in orbit around the sun. This is a gravitational force. We have a pretty good understanding of what the gravitational force is until we peel beneath our first level analogy, and then we have no idea what gravity is. Curvature space-time force, it's one of the 4 forces. The next force we find is the electromagnetic force. The electromagnetic force is the one responsible for electricity and magnetism. We're pretty used to electricity. We have this in our house, we have the lights. We know what electricity is, moving electrons. And we have magnetism. Magnet sticks on fridge and does a bunch of other things as well, but magnet sticks on fridge. And there's something related to magnetism and cutlery at a restaurant that is a tangent I am not going to go down, just dropping words there, not going down that tangent. So, next 2 forces, we have the weak force and the strong force. These are the nuclear forces. The weak force, as the name implies, is weak. And the strong force is the one that glues everything together. If you go down to the individual quarks, you have quarks that are glued together with the strong force. And then if you look at how protons and neutrons are glued together, then you have the strong nuclear force. Some people make the distinction of strong force and nuclear force, but they are basically the same in this context. And then we have the weak force, which is responsible for radioactive decay. Now, most of the particles we know of interact with at least 1 or 2 of these forces, and mostly with the electromagnetic force. Now, dark matter interacts gravitationally. it does not interact electromagnetically. We don't think it has strong interactions. And if it has weak interactions, they have to be very, 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 very weak, or we would have found dark matter by now. And I'll get to that later. But the question, is there anything else that does the same? Neutrinos. Now, neutrinos, this bottom family that was in like the fourth row of my standard model particle physics that I showed, neutrinos interact via the electromagnetic force. Sorry, no, neutrinos interact via the gravitational force, but they do not interact via the electromagnetic force. They also do have weak interactions. So at this point, you could say neutrinos, okay, it's something that sounds like it could be dark matter, right? It's interacting in the same way as dark matter does, or not interacting in the same way that dark matter doesn't interact, right? So it's a valid question to ask of, could neutrinos be dark matter? But here's the problem, or the fun thing. Neutrinos travel almost at the speed of light, and they are almost massless. In fact, in the standard model of particle physics, we expect neutrinos to be massless, to have no mass. Our standard model predicts that neutrinos have no mass. However, we have a lot of experiments that show that actually neutrinos do have mass. Very, very small mass, but neutrinos do have mass, which is already proof that the standard model is incomplete and that it needs extensions. If anyone thinks the standard model is perfect, neutrino masses proves them wrong immediately. And going off on a tangent here. So neutrinos do have a very, very small mass. Now, neutrinos travel almost at the speed of light. They can travel at the speed of light because if they did, they would be massless. But because they have this slight mass, they travel just beneath the speed of light. But the point here is they travel really, really, really quickly. And one thing we know about dark matter, which I'll get to how we know this later, but one thing we know about dark matter is that it helps build galaxies, it helps things form, it helps form structures in the universe. And it does this by basically sitting down and letting things fall on top of it, attracting things via the gravitational force. If you have a clump of dark matter that's moving slowly, things are going to cluster around it and form galaxies. Now, if all of the dark matter were traveling at the same speed as neutrinos, we wouldn't have galaxies in the universe. Things would be moving way too quickly, and you wouldn't be able to form anything. So the fact that we can see galaxies, that we can see structures in the universe, means that dark matter cannot be traveling practically at the speed of light, which means neutrinos cannot account for the dark matter. Now, some people say, okay, neutrinos could account for a small part of dark matter. Now, one thing we can actually do is we can calculate approximately the energy of neutrinos in the universe. And if you do this, you come out with a number that is much, 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 much smaller than the energy density we need, the amount of mass we need to explain dark matter. So two things here. Neutrinos wouldn't allow matter to cluster, and neutrinos there just aren't enough neutrinos to explain dark matter. So then some people say, okay, neutrinos could be a very small component of dark matter, like a very, very small part of dark matter, but they can't be all of the dark matter. So we don't think that most people don't count neutrinos to be dark matter, but neutrino masses do prove that we need physics beyond the standard model. So primordial black holes, great question. Making a note of that. Scott, I will get back to primordial black holes later. So we know that dark matter exists. 25% of the universe is in the form of dark matter. But now we have to ask the question of, how do we know this? So what I've told you so far is dark matter doesn't interact via the electromagnetic force. It's invisible. Dark matter interacts via the gravitational force. Dark matter cannot be neutrinos, or neutrinos can't be all of the dark matter. So how do we know these things? Where does this knowledge come from? How do we figure this out, given that we cannot directly see dark matter? And I'm sure the regulars know what is coming now, and it's taken me almost 20 minutes today. The biggest piece of evidence we have for dark matter comes from the CMB, the cosmic microwave background radiation. What you can see here on the screen is the oldest light in the universe that we can see in any direction we look in the night sky. This is the background radiation that is behind everything else in the universe. Now, this background radiation was produced when the universe was 380,000 years old. So this means it's over 13 billion years ago. So in the early universe, you have three main components, four components. You have protons, you have photons, which are particles of light, you have electrons, and you have dark matter. The dark matter is not doing much. It's just sitting there and clustering. Stuff is falling on top of the dark matter, just interacting gravitationally. But the other three are constantly bumping into each other. So the protons, the electrons, and the photons, the particles of light, are constantly bumping into each other. So light can't really travel. Imagine, light is trying to make its way through a crowded room at a party. You go into a party, a crowded room, you want to try to cross the room, you just bump into people. Excuse me, let me through. COVID carrier, let me through. That would clear the room for you. Anyway, I'm sorry for that comment. That was uncalled for. So if you're walking through a busy room, you can't really cross it easily. And that's a problem that photons have in the early universe. They can't travel because they're constantly bumping into to the electrons and to the protons. So the photons can't travel freely. Now, as the universe gradually cooled down, the protons and the electrons could combine together to form hydrogen. And at this point, the photons can no longer interact. They've kind of coupled up. The photon is now free to travel through the room because everyone's grouped together in little couples. So now the photons can travel freely throughout the universe. So the photons break away and start their journey through the universe, and they've been traveling ever since to where we are today. This light has been redshifted, so it's now in the microwave range. So we have this cosmic microwave background radiation, which means it's everywhere in the universe, in any direction we look, and currently in the microwave range of the electromagnetic spectrum. Now, the thing that's really, really cool about this is it contains all of the information, all of the statistical information of what the early universe looked like. Because since these photons broke away and started traveling towards us, they haven't really done much else. They've just been traveling. They feel gravitational effects. They get shifted around a bit if they go close to a galaxy. But otherwise, they've basically been traveling uninterrupted. So when we look at these photons, we can understand what the early universe looked like. And I mentioned before that dark matter in the early universe is just sat there, gravitationally attracting things. So if dark matter is gravitationally attracting things, it's going to attract the protons. The protons are going to be attracted there. So are the electrons. So when the photons break away, the way they travel through the universe is going to change depending if they were in a clump of dark matter or away from dark matter. So by looking at the CMB, by looking at this cosmic microwave background radiation, we get a snapshot of what the universe looked like 380,000 years after the Big Bang. And by taking the statistical properties here of these slightly hotter photons in red and these slightly colder photons in blue, what we actually get from this is that the universe needs to have 5% normal matter, 25% dark matter, 70% dark energy. If you change any one of those numbers, you're going to change what the CMB looks like. So based on the CMB, we know that dark matter has to be there. But the CMB was actually not the first way that we came to think about dark matter being there. I am going to come back to the primordial black holes. I've made a comment of it, but Jasmine's just given an answer as well. And Jasmine is also a physicist, so you can trust Jasmine's answers as well here in the comments, but I will get to primordial black holes in a minute. So for now, I'm just doing general things about dark matter that we can know about from the universe, and then I'll get into what this tells us about what dark matter actually is. I do actually have a plan today. I know it looks like it's all hand-wavy and made up, and it mostly is, but occasionally there is a plan. Very, very, very occasionally, and sometimes I even remember the plan. And I am absolutely rambling while I try to find the right image, and that definitely works. So the first piece of evidence we actually had for dark matter is what is known as rotational curves. Now, rotational curves is what you get when you look at the motion of stars around a galaxy. So what you can see here on the horizontal axis is how far away we are from the center of the galaxy. And what you can see on the vertical axis is the velocity at which, or the speed at which these stars are rotating. Now you can see in this dashed white line, we have the idea of this is what's expected from the visible matter that we can see. And then you have this other line much above, which is what we actually measure. So one thing we know about matter in the universe and in general is the further away you are from an object, the slower you should spin. This is something we can test very easily on a merry-go-round. If you go to the center of the merry-go-round, you feel a different kind of motion to if you're on the outside. If we look at the planets orbiting around the sun, Mars is moving around the sun slower than the Earth is because it's slightly further away. Jupiter is moving even slower. Mercury is moving around the sun much, much faster. The closer you are to the central gravitational object, the faster you move. So when we look at stars moving around a galaxy, we would expect the same behavior, that the closer they are to the center of the galaxy, the faster they move, and the further out they are, the slower they move. However, what we've actually observed is that it is practically flat. So if you take a star at the center of a galaxy and halfway out on what we think is the side of the galaxy, they are rotating at approximately the same speed around the center. And this is something that we cannot explain with what we currently know, unless well, there's other explanations as well, but one possible explanation for this is that you actually have a halo of dark matter. So we have the galaxy disk here, and you have a big halo of dark matter around it. So that when we say this star is on the outskirts of the galaxy, this actually isn't true, because there's all of the mass of the dark matter that is keeping everything in motion. It's kind of all of the thing is moving together because of the mass of the dark matter. And rotation curves is one of the ways we first came to understand the existence of dark matter. For this, Vera Rubin's work was pioneering and essential, and Vera Rubin is considered by many one of the first people to ever find evidence of dark matter. Now, Vera Rubin did not win a Nobel Prize for reasons that I'm not going to go into today, but you can be damn sure it was politically motivated. Okay, few comments here. Is it possible that better telescopes like JWST will change our estimate of how much normal matter there is? Making a note of that, Paul, because that's a great question. I will come back to that one as well. I'm actually even writing questions down today because I do want to say a few things in order, and then I'll come to these questions. Change how much visible. I write questions down in short form and then stare at them like, what did that mean? That sounds like Newton's issue with Mercury's orbit. Yeah, and then it turned out that Mercury was going back and forth and back and forth. But we've been able to see that this is a pattern that we see in every galaxy that we look at. Regardless of which star in the galaxy you pick, you find the same issue. So, two things that we now know about dark matter. It's clustering gravitationally, so it affects the CMB. The CMB tells us how much dark matter there is. The first way we were able to observe dark matter was via rotation curves. But one of the biggest pieces of evidence we have for dark matter, I really should have reorganized my slides into a better system because today the slides are all over the place. One of the other biggest pieces of evidence we have for dark matter, do we know how dark matter is distributed within a galaxy, uniform or something more complicated? That is a great question, Jasmine. Short answer is we don't know. Now, we have a pretty good idea as to how what we call the density profile of dark matter should be. So the density profile tells you how dense dark matter is as a function of how far away you are from the center. So how much dark matter is clustered, basically. Now, we've been able to see that overall, dark matter does seem to follow what we call an NFW profile, and that's a technical term, but it basically means it's more peaked in some places and then gradually drops out. We have observed a lot of differences in this, but overall we have a pretty good understanding, we think, of how it should behave. It doesn't match our simulation, so what we expect doesn't actually happen in terms of how dark matter is distributed. So we have a good idea as to what should happen, and the simulations and the observations are not completely aligned, but it's not a big problem. So we don't know exactly how dark matter is distributed in galaxies, but we have good guesses and pretty good estimates based on what we've been able to see. Then if you add dark matter with self-interactions, the picture changes, and then the simulations and observations come closer together. So it's a great question, and there's not a short answer to it. But the short answer I'm giving is we have a pretty good idea, but it's not perfect. Okay, so dark matter can be measured with the rotation curves. Dark matter can be measured not directly, but based on the CMB, we can get how much dark matter there is. Based on things like rotation curves, we can get an idea that dark matter should be there, and we can put general ideas as to how dark matter should behave within a galaxy, and how much dark matter there should be in galaxies. So we can get ideas here. But one of the biggest pieces of evidence we have for dark matter, and one of the biggest ways we can study it. So just to just want to make a summary statement here. So I started by saying dark matter is invisible. It doesn't interact with light. So all of these pieces of evidence that I'm talking about rely on the gravitational force. Oh, wow, this is a strange tea. I have a new tea. And it has a bunch of things in it, including vanilla, and vanilla does not belong in tea. That said, it's actually not bad. I like my vanilla, cinnamon, rooibos, chamomile tea. Anyway, You will get to learn about my fun tea habits here because I always comment on my teas live on the streams. So everything I'm talking about, rotation curves, CMB, all of this is gravitational ways of measuring dark matter. Because if dark matter doesn't interact with light, we cannot see it. So we have to go to something else. Like, okay, so if we can't see it, what can we do? And we can see the effect it has on other things. So we don't see dark matter itself, but we see a lot of other things moving in a way that tells us, okay, there must be some object here with mass that is affecting everything, and it's some object that I can't see. And when you have something you can't see that has mass, it sounds a lot like dark matter. And if it sounds like a duck and walks like a duck and swims like a duck, you can probably call it a duck or a pig or whichever animal you want in that analogy. Vanilla sounds better in tea than cucumber. Yeah, the cucumber tea in me, I got through a whole box of it. I haven't bought it again. But this is a new tea that I didn't actually intend to buy. I thought I was buying a mix of green tea. There was weird Finnish writing on it, and I bought a mix of teas that are not all green. There's like green tea, white tea, black tea, and the rooibos chamomile vanilla thing. Anyway, if dark matter affects how galaxies move, then the galaxies would also affect how dark matter moves. Yes, indeed. Now, the thing is, there is a lot more dark matter than normal matter. There's 5 times more dark matter than normal matter. If we go back to our pie chart, right, we have 5% normal matter, 25% dark matter. So while normal matter is going to affect the dark matter is going to be the one kind of determining how galaxies move. So then the galaxy, if we define a galaxy as having like all of the visible matter of the stars that we see, plus this big halo of dark matter, the dominant part that controls the motion is going to be the dark matter. So you do have a vice versa effect, but like Newton's second law, for every action there is an equal and opposite reaction. But the normal matter is affecting the dark matter is affecting normal matter, but there is a factor 5 there, so the dark matter is kind of the one in charge of what's happening. Now, one of the biggest pieces of evidence we have for dark matter, and something that gives us a lot of information about dark matter, is when clusters of galaxies smash together. So if you have a big cluster of galaxies and another cluster of galaxies, and they come together, which happens in the universe because of the gravitational force, you're going to have a lot of gravitational things happening here. Now, the good thing is that most of galaxies is empty space. So if you imagine that, I throw sand with one hand and sand with another. So I have 2 handfuls of sand and I throw it at each other. Most of the grains of sand are not going to touch. They're going to pass each other by because, when I throw the sand, there's going to be a cloud and a cloud of sand, and some of the particles sand grains might bump into each other, but most of them will just pass by. So when you have a cluster of galaxies crashing into another cluster of galaxies, most of the galaxies are not going to see each other. They're just going to be like, bye galaxy, they're not going to merge together. Some might, but overall, most things will pass by. But we will get an effect when you when you smash galaxies together, you will get friction. So a lot of the space in galaxies is made up of hydrogen gas. So this like superheated gas, and not superheated, but this gas, this hydrogen gas or cloud, dust, whatever you want to call it, which is around the galaxies. And this does feel pressure effects. So as these galaxies come together, any dark matter in the galaxies would move by without feeling each other too much because it's too far away for the gravitational force. But a lot of the gas will get dragged back. So we're going to, merging of 2 clusters of galaxies, you have different effects. You have dark matter passing by because the things are too far away to gravitationally pull each other. But you also have the hydrogen plasma gas heating up and causing friction. Do you think there are dark people wondering where 25% of the energy of the universe is? I love the thought of dark people, and I'm also making a comment of that, like invisible people. I'll come to that later. Of course, the grains that do hit are on a very bad day. Yeah, exactly. If your galaxy happens to be the one that hits another galaxy, I'm sorry for you. Merging of clusters of galaxies. Oh, I don't have my nice cheat sheet here, but that's fine. I have another version of this where I have a cheat sheet of what I'm supposed to say about this image, and I don't have it in this version. So what you can see here is the bullet cluster. The bullet cluster is the most famous example of two galaxy clusters smashing together. We call it the bullet cluster because the one on the right, the slightly smaller one, looks like it had a bullet effect when it passed through. So there are 3 different colors to pay attention to here. Everything that is white, yellowish, this is visible matter taken by a normal telescope, I believe Hubble in this case, and all of this is the matter we can actually see. What you can see in pink is the infrared, sorry, the X-ray, which gives us an idea of where the hydrogen gas is, so where the gas is. And what you can see with the pink one is, as expected, the gas is having this effect that as the clusters pass by, the gas started heating up and moving close together. So you have this drag effect, which you see in pink. Now, pink is not the real color, we've just colored it in pink to highlight what we're talking about. So yellow, white, stars, all of that visible matter. Pink is where the gas in the galaxies is. Now, what you can see in this bluish purple is actually where the dark matter, or sorry, where the most mass is. So one thing we know how to do is figure out how mass is distributed. So if you have more mass in one region or less mass in another, this is something we're pretty good at figuring out. And I'll explain why in just a sec on the next point. I should have reversed these two, but this is something that we're pretty good at figuring out, of where mass is. So what the blue one is showing us here is if we measure where the mass is distributed in this cluster of galaxies that merge together, we get the blue/purple thing. So we have three things here: white, yellow, visible matter. Purple is where the gas is, but blue is where most of the mass is. So what this is showing us is that most of the mass does not actually align with the visible mass or with the gas. So this is telling us that when these galaxies smash together, most of the mass was not in visible matter or in stars, but instead it was in type of matter that does not interact via the electromagnetic force, or it would have been dragged, but does interact via the gravitational force, because we can see that there is mass in these two places. So the bullet cluster really shows us that most of the parts of our galaxies is actually invisible matter. Invisible matter that doesn't interact with light and that interacts gravitationally. Again, we're starting to sound a lot like a duck here, so we call this dark matter. And there are many other models or many other things that try to explain rotation curves. You can explain the rotation curves of galaxies by modifying how Newtonian gravity works. But trying to explain the bullet cluster, that gets tricky for anything that is not dark matter. And trying to explain together the bullet cluster and the CMB, that is very difficult. And no other model except dark matter yet has been able to explain the CMB and the bullet cluster. So a lot of people ask the question, like, have you just tried changing gravity? Why do we need dark matter? Is it just a fudge factor? It's like, yes, believe me, we've tried. But no amount of changing gravity has been able to explain the CMB or the bullet cluster. And for that, we need dark matter. Okay, question from James that I see Jasmine's already answered as well. If we could flip a switch that made dark matter interact with other matter, would we notice from the solar system scale? Yeah, so if you suddenly turned on dark matter, we would have a problem. If you hold up your thumb, every second, 60,000 neutrinos zip through the tip of your thumb. Every second, 60 million. 60 million neutrinos pass through the tip of my thumb every second. Dark matter is probably doing more than that. So assuming dark matter is more or less evenly distributed in the universe. Now we know there's more dark matter in galaxies and less where there's not galaxies. It's very likely that there is dark matter zipping through this room right now. So if you suddenly make dark matter interact, we're going to start having a bad day. Maybe your first particle of dark matter you won't notice. But at some point, depending on how you're making it interact, if you're making it interact with normal matter in a way that emits photons, you're going to get a lot of radiation suddenly. So don't turn on interactions with dark matter just yet, because it would probably be a bad day for us. Okay, so I just mentioned that one of the neutrinos know not to bother me if I don't bother them. Exactly. We have a nice relationship with neutrinos. We let them do their thing. They let us do our thing. We try to study them occasionally, but from a distance, like, hey, neutrinos, hi. Neutrinos are chill. They don't bother us much. So I mentioned just now with the bullet cluster, we know where the mass is distributed. So we can ask the question of how do we know where the mass is distributed? And the answer is gravitational lensing. Now, gravitational lensing, I have no idea at this point if I need to go back or forward with my images. I've lost track of where I have all my images. Aha! It's going in the right direction. Gravitational lensing, oh, I don't need it just yet, is what happens when you look at the light coming from a distant star. Now, we know from Einstein's general relativity that objects with mass bend spacetime, and the curvature of spacetime tells objects how to move. So if you have an object with mass that is bending spacetime, even if you can't see it, if it's dark matter, visible matter, it doesn't matter. It's bent spacetime, so anything traveling through that curvature of spacetime will be distorted. So imagine you have a distant galaxy, and this galaxy is sending its light towards you. Now, on its path towards us, if these light beams encounter a big gravitational object, they are going to be distorted around it. So what that means is you get gravitational lensing. So here I have a sketch of it. Bottom left, you have planet Earth. In the top right or rightmost part of this, you have a distant galaxy. This distant galaxy is sending off these light beams that we show as light. Now, on its path towards us, it finds this big object in the middle that has this kind of blue aura. This is something that we might not necessarily see, but it's something that has mass. It's distorting the path of the photons. So you see the two white beams here get distorted around this object with mass. And then by the time it reaches us, we trace back this image, and we end up with two different positions. So instead of seeing light coming from one source, we're now seeing light coming from two different places. So it's basically like holding up a wine glass to the light. You see the light distorts. If you've ever looked at a light bulb through a wine glass, you'll see that it distorts. And now we're doing the same, but instead of holding up glass, we're holding up some gravitational object. And this acts as a gravitational lens and distorts the image from behind it. And this is something we can actually see in the Hubble Deep Field images, and incredibly in the JWST Deep Field image, that spectacular image. But for now, I'm going to use a Hubble one here. This is the classic example we use when we're talking about gravitational lensing. Now you can see there's a lot of galaxies here that have this very distorted effect, and it really does look like we've just held up a lens to the night sky. So what gravitational lensing can tell us is, okay, there's an object with mass that is distorting the light coming from this distant galaxy, but I can't see this object, because if I could, it would block the light coming from the galaxy. So there's something that is distorting this background light that we cannot see, something that is invisible, interacts via the gravitational force. Once again, it sounds a lot like dark matter. And gravitational lensing is how we were able to figure out where the mass is in the bullet cluster. Recap time. Dark matter, invisible, interacts via the gravitational force, doesn't interact via the electromagnetic force, which is why we call it invisible. Affects the CMB, affects the rotation curves of galaxies, affects gravitational lensing, bullet cluster, how clusters move. All of this is stuff that are gravitational effects. And there is one more thing with dark matter. You don't own any wine glasses because I'm not an alcoholic. Good for you. I actually drink wine probably once a year, and I own 6 wine glasses so that when I have people around, I can offer people wine. And then I have wine glasses to do experiments with. But even if you don't own a wine glass, if you ever have a wine glass, just hold it up to a light, and you can see this cool lensing effect. Only do the wine glass thing with an empty glass. Yes. If you spill wine on yourself or on your laptop while you're trying to hold it up to a light, please don't blame me. I'm not advertising that you should throw wine at each other or on your laptop. So please do it with an empty wine glass, as Beth just pointed out here in the comments. Now, going back to the early universe, when I told the story of the CMB, I mentioned that dark matter just kind of sat there and stuff is falling on it. And I explained how this affects the CMB, but it also affects the protons and the electrons, or the hydrogen. Because dark matter is just sat there clustering, the hydrogen, as it starts to form, as the protons and electrons combine together, it's falling on top of the dark matter. So suddenly you have dark matter and you have hydrogen coming around it. So what this means is you have a lot of gravity in one place, you're accumulating hydrogen, and you're pulling everything together, so you have a lot of pressure. And if you put enough hydrogen in one place, you add some pressure to it, you can form a star. You do this enough, you form a galaxy. So by this logic, the places in the early universe where there was more dark matter, now you're more likely to find galaxies, because dark matter was setting the scaffolding for everything else to build upon. So this really very cool idea gives us what is known as the cosmic web. So, based on all of our knowledge or all of our current understanding of dark matter and normal matter, we'll have wine glasses when we do Drunk Cup of Cosmology stream someday. Yeah, someday we're all going to get drunk together, and only I'll be on camera, so I'll be the one suffering the consequences. But yeah, someday we do Drunk Cup of Cosmology. Maybe I get a guest to join me. You've lost 15 pounds. If you wanted to do that, great. If not, I'm sorry for you. But yeah, beer does have a huge effect on weight. It's very curious how beer works like that. It's liquid calories. Anyway, I am not in any way a nutritionist. Please don't take any advice on me in terms of alcohol or food consumption, because my advice is going to be eat all the cinnamon buns. There's so much to figure out in so little time. Yes, I agree. There's too much to do, not enough time, and you can't fit enough hours in the day. But if you take all of our understanding of dark matter, that was not a but to the previous sentence, but to the previous sentence. If you take all of our understanding of dark matter, what we think should happen, you can put it in a box, in a computer simulation. You run a simulation and say, show me what the universe should look like. Favorite dark matter candidate? I'll get to that when I get to actual dark matter candidates. I know I'm 46 minutes in, running out of time, but I am still on track with what I want to say, mostly. And I have a bunch of questions written down that I am going to come back to, including primordial black holes and dark people and space dragons. That's not written down, but we'll come back to space dragons. If you take all of your knowledge of how things should move, based on dark matter, based on what we know of gravity, you throw it in a box, you run a simulation of what the cosmic web should look like, and this is what you get. This is the Millennium simulation. Every dot here represents a galaxy. So what you can see is darker regions where there's no matter, and very, very bright regions where there's a lot of matter. And it goes together in this nice cosmic web. So what this image shows us is, if what we've understood so far about dark matter is correct, this is what the overall structure of the universe should look like. Where these lines meet, you have galaxy clusters. Each point here is a galaxy. Where you have the darker regions, you have voids. This is what we predict. This is a simulation. Based on our understanding of dark matter, this is what we expect. And now I can show you our actual measurements. And what you're seeing here is the actual measurements from the Sloan Digital Sky Survey, a survey that basically figures out where galaxies are in the night sky. And it goes out to redshift 0.14. So this is looking back about a billion years into the past, 1.5 billion years. And you can see here, every dot represents a galaxy we have actually measured. So there are two black triangles, because that is where the Milky Way lies. So this is looking up from the Milky Way and down from the Milky Way, because the Milky Way is kind of blocking our view in the horizontal plane. So we look up, we look down, and we get this nice cosmic web. So if we compare our simulation here with our actual observations, you'll see very, 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 very good agreements. And this cosmic web, this structure that we have, this intricate, nice network, is really something that we explain with dark matter. Bringing it around from the top, dark matter, invisible. How do we study something that's invisible? We ask the universe. And what does the universe tell us? Well, the universe tells us dark matter affects the CMB. So we know from the CMB that there is 25% dark matter. Dark matter affects the rotation curves of galaxies. It affects gravitational lensing. It affects how galaxies smash together in bullet cluster style things. It affects how matter is distributed throughout the universe. So by looking at the universe, we get a lot of information about dark matter. But now we still have the big question to answer of, what is dark matter? It's something that interacts via the gravitational force. It's something that has mass. It's not neutrinos, so what is it? This is where it gets tricky, because it's very hard to figure out what it is. What we are very good at is figuring out what it isn't. Like, we can say dark matter cannot be this, because otherwise it would have this effect that we haven't observed. But saying exactly what dark matter is kind of requires picking up dark matter and saying, hey, look, I found dark matter. So dark matter can be pretty much anything. And we also don't know how massive dark matter is. We have limits, but our limits cover 80 orders of magnitude. So dark matter could be a particle as small as an electron, or it could be an object as big as a black hole, and it could be everything in between. So there are some fun models that we don't like to talk about. I often make the comment with space dragons. Like, we can probably say that dark matter is not space dragons because we might have seen space dragons, but dark matter beyond that, it's very, very difficult to narrow down what dark matter is. There are a bunch of different candidates. If you want some of the bigger ones, we go to primordial black holes. So primordial black holes are black holes that are formed in the very early universe. So when we think of a black hole, normally we think of a star that has collapsed. But you can also make black holes in the very early universe. If you have a region of space-time that is so dense, it can automatically collapse or directly collapse. It can form a black hole. And the cool thing is these primordial black holes, if they existed, could be in the range of mass that could be detectable by LIGO. There are some people who think that what we've measured at LIGO could be primordial black holes. So could dark matter be made up of primordial black holes? Maybe. That's a hot topic. That's a topic of debate. Every week you get a new paper. Some people say, yes, dark matter can be made up of primordial black holes. Some people say no. There was a time when we thought that it couldn't be primordial black holes because else we would get too much lensing. But by now, there are ways to get away of that. So, as Jasmine said earlier, primordial black holes at some point were ruled out as being 100% of the dark matter. Now that analysis is questionable. But yeah, it's we're not really sure if primordial black holes could or could not be dark matter. Depends who you ask. Dark matter is that thing that does all the stuff Diana just said. Yep, that's what dark matter is. It's the thing that does all of these things. But dark matter is not the thing that we're after, right? The effects of dark matter is not what we're after. We're after dark matter itself. So it's like, yes, it does all of these things, but what is it? That's still what we want to know. But yeah, my favorite dark matter candidate is space dragons as a joke, but it's not my actual favorite one. So on the one hand, we can have primordial black holes, but then you can also go down to particles and ask the question of, could dark matter be made of particles? And I began this stream, or at some point in the stream, I showed the standard model of particle physics and said, these are the building blocks we have. And there are 17 building blocks for that 5% of matter that is the visible matter. So it's a valid question to ask, but could we have similar building blocks in the dark matter sector? Could we have particles that are the dark matter? And then you put enough of them together and you can explain all of dark matter. So whatever processes form the galaxy, form galactic black holes, and form dark matter, not necessarily. We don't know what created dark matter. Just at some point, dark matter was there. We're still trying to figure out the interplay of how black holes and galaxies, like which came first, a supermassive black hole at the center of a galaxy or the galaxy. We're still not sure which came first. There's definitely a chicken and egg debate there. So yeah, every galaxy has a supermassive black hole at the center. Which came first, the supermassive black hole or the galaxy? We're not sure. Now, we did name the galaxies first, so linguistically, the galaxy came first. But I think from a scientific point of view, maybe the supermassive black hole came first. We're not completely sure about that. But dark matter could be made up of particles. And there are a lot of different candidates when you get down to the particle side of things. For an example, you could have WIMPs, weakly interacting massive particles. Now, weakly interacting massive particles, as the name implies, they interact weakly, they're massive, and they're particles. And this is probably the most well-motivated candidate. Because from a theoretical point of view, if you construct WIMPs, you automatically get the right energy density, so the right amount of dark matter based on what the CMB tells us. So that made WIMPs very, very, very interesting. And WIMPs is what we've been looking for at a lot of experiments. And we haven't found them yet. Despite a lot of experimental effort, we still have not found WIMPs, which makes it kind of difficult to continue searching for WIMPs. But you can get away with, like, if you change how WIMPs behave very slightly, then you can get around the constraints. Another idea is that dark matter is made up of axions. Now, axions are a different type of particle to WIMPs. They have slightly different behavior. And the cool thing is we know how to look for axions. So that's something we can do. We are doing it. We haven't found them yet, but we haven't pulled them out either. Then you can also do fun things of what if dark matter is particles that are produced from primordial black holes in the early universe evaporating, because any black hole at some point, if it can basically evaporate, loses its mass by a particle creation on the event horizon, black holes can evaporate. And if primordial black holes in the early universe evaporated, they could have produced dark matter. But that dark matter would move a bit faster than other matter. So then we can put limits on how much of the dark matter could have come from a black hole in the early universe. That's a paper of mine. It's really fun. So what is my favorite dark matter candidate? I don't have a favorite. I don't play favorites. At least this is my diplomatic answer. I think primordial black holes are really interesting. I think WIMPs are really interesting. I think there's still a lot the universe can tell us about dark matter. But there's also, we had the comment before about dark people that I wanted to come back to. Because, we have a huge amount of structure. We have people, we have galaxies, we have planets. All of this is stuff we can see with visible matter, but we know that's only 5%. Dark matter is 25%. So there's a good question we can ask of, can we have a standard model of dark matter? So our model of particle physics, but for a dark sector. Could we have an equivalent to the electromagnetic interaction, but in the dark sector? Can we have the equivalent of a weak and a strong interaction, but in the dark sector? And if the answer is yes, then can you form bigger things? Can you form, for example, a planet made of dark matter? Can you form dark matter nuggets, like the size of a chicken nugget, but made of dark matter? There's actually papers on dark nuggets. How big can you go? Could you have a person made of dark matter? Are there dark physicists out there wondering where the remaining 5% of the universe that they can't see it because they wouldn't be able to see the visible light? Is there a dark physicist in the room with me now? Probably not. We can put limits on how big dark matter can be and how many interactions it could potentially have, but these are all just guesses. So at some point, it becomes quite complicated. Now, I don't think there are people made of dark matter, I really don't. But it's a fun sci-fi question to ask. I wonder why no sci-fi author has done the thing of, we want people to be invisible, let's make them of dark matter. I would be sold on that. Like, I would pick it apart physically. Maybe I should just write that myself. Would the evaporation from primordial black holes be the same kind of energy as from other kinds of black holes? Yes, it's still Hawking radiation. The only thing that changes between a primordial black hole and a stellar black hole is how it's formed. But once it's formed, it's a black hole and it's going to behave like a black hole. It doesn't matter where it is. So there are other models of dark matter that say that dark matter is the interaction that we feel from a higher dimension or a different dimension. So then you can go to higher dimensional dark matter. Like maybe it's just rolled up in a dimension that we can't see and putting pressure on our universe. We can't rule that out. So there are a lot of ideas, a lot of possibilities for dark matter. And I realize I'm almost out of time and I still want to talk for about 10 minutes. So we're just going to go for a slightly longer stream today. Hope everyone has snacks and coffee and tea because we're going for more than an hour today. So if dark matter is particles, before I get to that, there was the question earlier of, can the JWST change how much visible matter we know of in the universe? And the answer is probably not. Because this amount, when we say 5% normal matter, 25% dark matter, this comes mainly from the CMB. And the JWST is not going to change our measurements of the CMB. Now, we might find more galaxies than we haven't seen before. We're definitely going to see galaxies we've never seen before because the JWST can peer back further in time. But it's not going to change the amount of matter because this is not counted based on the galaxies we see, but rather based on the statistical properties of the early universe that we get from the CMB. So it doesn't matter if you suddenly visually see 20 more galaxies that you didn't see before, because those are already accounted for in the statistical properties of the CMB. So I do think I've answered all of the questions that I wrote down, but I know that were not all of the questions. So if there's a question you asked that I haven't yet answered, please ask it again, because by now I'm not going to scroll back through all of the questions. I think I got to most of them. I know there was a comment that my favorite dark matter model is space dragons, and I'm happy to go with that. But yeah, if you've asked a question and I haven't answered, please ask again. because I don't have any more written down at this point. But I still want to talk about dark matter. So if dark matter is a particle, the big question we have to ask is how can we find it? Because now we're talking about finding a particle, and this is tiny, subatomic, and then we can no longer rely on gravitational interactions, because once we get down to the quantum world of individual particles, we can't talk about gravity because we don't know how to put gravity with the quantum world. If anyone does, please let me know, but currently we don't know how to do it. But what you can count on here, this show was too Socratic, too many questions and not enough answers. Yeah, we have lots of questions today and not many answers, but that's the life of a dark matter physicist. So many questions, no answers. We're getting there. I also, yeah. So, if dark matter is made up of particles, the WIMPs, whatever type of particle they may be, how do we study this? And now we can rely on one thing. And the earlier in the history of the universe we go, the higher the energy. In the very early universe, we had a lot more energy. As the universe expanded, it cooled down, the energy went down. Now, we don't need to worry about conservation of energy here. We're just talking about this energy kind of being dissipated as the universe grows. But what it means is the overall temperature of the universe has gradually been decreasing. I mentioned before as well, at some point we had protons, photons, and electrons bumping into each other, and as the universe cooled down, we could form hydrogen. So this cooling down means that the overall energy decreases. So if we go further and further back in time, we go to higher temperatures and higher energies. The reason this is important is because once you go to high energies, or said another way, when you go to the early universe, this is the point when the interactions were more noticeable, when the individual particles were more dominant. You had to worry about whether photons were talking to electrons or not. Today, we don't need to worry about this. The universe is cooled down enough that we have a general fluid that we call dark matter, or a general gas that we call not visible matter. But in the early universe, the fundamental interactions between particles are significant. And the further back in time you go, the truer this is. So the higher energies you go to, the truer this is. So then if we want to understand the particle nature of dark matter, what we need to do is go to higher energies. And this is exactly what we try to do in a lot of our experiments. If we go to higher energies, we can replicate the conditions of the early universe. And I don't want anyone to be worried when I talk about high energies, because a high energy for a particle is less than a bolt of lightning today. So the Large Hadron Collider is the biggest particle collider we have that is smashing particles together and trying to find dark matter. And it's at very high energies, and you might have heard about a potential future collider at even higher energies. In one collider run, in one like smashing of particles, there's less energy than if you have a lightning bolt. So it's really high energies for an individual particle, but not overall high energies, not something we need to worry about. But the idea of the Large Hadron Collider is if you smash particles together at high enough energies, you might be able to reproduce some of the conditions we had in the early universe when the individual interactions are more important. And at this point, you can study the particle physics nature of dark matter. And this is what we try to do in colliders. This has already given us a huge amount of information. These collider experiments where we're smashing protons together, they let us find the Higgs boson, because if you smash particles together, you're not just going to create dark matter, you're going to create standard model particles as well. So if you smash enough particles together, you're going to get Higgs. If you measure enough Higgs, you can say, hey, look, we found the Higgs boson. And if you smash enough particles together, you're going to get other things coming out. We know that if we smash these things together, there are different chains, different reactions that take place. We find standard model particles and dark matter. So I know some people seem to think that, colliders have run their course, they've done enough, should we move on to something else by now? And I would argue absolutely not, because there's a lot of stuff that we expect in beyond the standard model theorems. And we know that the standard model is not complete. Standard model cannot explain neutrino masses. Standard model does not explain dark matter. Okay, it doesn't try to, it's a normal part, but it cannot not explain dark matter. So there are missing pieces in the standard model. We also don't know why there's more matter than antimatter in the universe. And these are things we can try to measure with collider experiments. So even though the LHC has given us a lot, and there are plans for a future collider that's going to go to higher energies and give us even more, and the potential for discovery is still very, very big. And I want to bring this back to one other thing. So far I've spoken about how we can use the universe to measure dark matter, how we can use colliders to understand the particle physics nature of dark matter, but there's two more ways we can go about studying the particle nature of dark matter. And now I'm going to bring up the famous make it, shake it, break it diagram. It's not officially called that, we've just decided, a bunch of us have decided it's called that. So what you can see here is the different possible ways a dark matter particle can interact. And you can read this diagram in three directions. So first of all, let's go right to left. So what you're seeing here in the middle is a schematic representation of what we call a Feynman diagram, which is itself a schematic representation of a particle interaction. So if we read this diagram from right to left, what we're doing here is we're smashing two standard model particles together, something happens and you produce dark matter. This is what we hope to do in collider searches, and this is the make it approach because you're trying to make dark matter by smashing standard model particles together. Then you can have the shake it approach, where you have dark matter and a standard model particle come together, bump into each other, and then go away their separate paths. So you start with dark matter and standard model particle, you end with dark matter and standard model particle. We're now going bottom to top in this image. And this is what we call the shake it approach because we're shaking the visible matter. So in the make it approach in collider searches, you smash standard model particles together. You measure all of the energy coming in, you measure all of the energy coming out. If something is missing on the way out, you know energy must be conserved. And if some energy is missing on the way out, then you say, okay, something carried off my remaining energy and it's something that I cannot see, it's probably dark matter or it could be dark matter. In the direct detection approach or the shake it approach, you build a huge detector and you hope that eventually a dark matter particle is going to bump into something in your detector and shake it slightly in a way that's going to produce a very tiny flash of light. So this is the shake it approach. So we have make it, you read from right to left, shake it, you go from bottom to top. And then you have the break it approach, which is the opposite to the make it approach. The break it approach is what we do in indirect detection. So now we're going left to right. Now for the indirect one, what you do is you say maybe somewhere in the universe there is dark matter. And if dark matter is its own antiparticle, so you have dark matter and anti-dark matter, this can come together and annihilate, and maybe it produces some standard model particles. So the indirect detection is the opposite process to the collider searches. Here you're trying to break dark matter. You smash dark matter together, you hope it disintegrates or annihilates into standard model particles. So then you create standard model particles that you didn't expect. So collider searches, you make dark matter, direct detection, you shake it, and indirect detection, you break it. Make it, shake it, break it. It does sound like we're trying to concoct some special drink here. We make it, shake it, break it. Shaken, not broken. Shaken, not stirred. Shaken, not maken. You can go through lots of Bond variants there. But these are the three main ways we have to find particle dark matter. Shake it, make it, break it. Make it, shake it, break it, sorry. And for the collider one, again, you smash standard model particles together. You see if there's any missing energy. If there's missing energy, it might have been carried off by dark matter. In the direct detection ones, you build a huge, massive detector like a tank of 10 tons of xenon. Xenon, yes. And you wait to see if something smashes into it and slightly vibrates everything. And in the indirect one, you count all of the particles you can see around you, and if suddenly you have more particles than you expected, maybe there's something producing them. One easy target here is antimatter. For an example, antiprotons. So we know there's not many antiprotons around because an antiproton and a proton, when they meet, they annihilate. But if you do have antiprotons, you can figure out what's causing them. There are two main things that cause antiprotons. One of them is pulsars, and the other could be dark matter. So what you can do is you can measure the amount of antiprotons you see in the galaxy, and then you can do a budget tally. Okay, I've measured this amount, I expected this amount, does it match up? And if the answer is no, if you have too many antiprotons, then there could be something else producing antiprotons, which could be dark matter. The cool thing is there's quite a few of these indirect dark matter experiments, but my favorite one is the AMS. And AMS is on board the International Space Station. So at some point in the early 2000s, on the outside of the International Space Station, astronauts installed a new particle detector that is just there measuring antiphotons and a bunch of other stuff and trying to look for dark matter. And I think it's really cool that we put a dark matter detector on the International Space Station. Bringing everything together. From cosmological observables, from the way galaxies move, from the CMB, from how matter clusters, from how things smash together, from gravitational lensing, we know that there has to be dark matter in the universe. We know that dark matter accounts for 25% of the observable universe. We know this from the CMB. We know this from the bullet cluster. We know that dark matter does not interact via the electromagnetic force, but it does interact gravitationally. But we still don't know what dark matter is. One possibility is that dark matter is primordial black holes. We are searching for them. Another idea is that dark matter could be axions. We are searching for them. And another idea is that dark matter could be other types of particles that are not axions. We are searching for them as well. And we do these particle physics searches via direct detection, where we make dark matter. Collider searches where we make dark matter, direct detection where we shake it, and indirect detection where we break it. And there's a question I get asked often is, how are we going to figure out what dark matter is? Is it going to be from particle physics? Is it going to be from cosmology? Is it going to be from both? And I think it's going to be from both. Dark matter is the perfect playground for both cosmologists and particle physicists to come together. Because we need particle physicists to tell us if our model of dark matter makes sense, if it's reasonable, and what we might see in a direct detection, indirect detection, and a collider search. We need cosmology because it is the best place where we can see the effects of dark matter on actual objects. We need this information to come together, information from cosmology, from astro, from from particle physics. So dark matter really lets us bridge all of these topics and bring it together. And it's always fun because I go to a lot of dark matter conferences, and you can pick out 100 people in the dark matter conference, and everyone there will work on dark matter from a different perspective. And all of these perspectives are useful and necessary if we're going to understand what dark matter is. So dark matter is the best place where we have multidisciplinary science. We bring together particle physics, cosmology, astro. And it's really cool that there are so many of us working on this. We still don't know what it is, but we are getting there. We are figuring out what dark matter isn't. And every time you roll out a model, you get closer to finding the true model. And maybe we build a future collider and we don't find anything, and then we can roll out a bunch more of dark matter models, and that also tells us things. And now, one big question that I'm going to leave that I was hoping somebody would ask, but it's perfectly fine that you did it because I'm going to ask it as well. If dark matter interacts via the gravitational force, I've mentioned already, how do we see something that's invisible? People who have come to some of my streams know that one of my other favorite topics that is not CMB and dark matter are gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. So one big question we can ask ourselves, which I'm not answering today, I'm just floating this question out here, is, can we use gravitational waves to study dark matter? And if so, how? And the answer to that question is left for a future stream. I'm sorry for that, but you got a whole extra 15 minutes today, an hour and 15 minutes of the stream. We went for a long stream today. But one question that I think is really, really interesting is, can we use gravitational waves to study dark matter? And if so, what are we going to learn, and how are we going to do this? And does it make any sense to do this? Those are all fun questions to answer, and I don't necessarily have the answer to all of them, but at some point in some stream, maybe not next week, but at some point we are going to come back to this topic, and then I'll say, like, hey, do you remember when I did that stream? So an hour and 15 minutes of build-up just to leave you on this big question that I'm not answering. But we covered a lot of stuff about dark matter. And if I can leave you with one takeaway, one thing to know about dark matter, we're pretty sure it's out there. And we are a curious species, and we are not going to stop until we figured it out. And that is why dark matter is one of my favorite things. Wait for 2 dark matter black hole collisions. That would be nice, right? Let's see what happens. Okay, an hour and 15 minutes, went a bit longer than usual. I had a plan, I mostly stuck to it. You have to be skeptic. If dark matter isn't very dense, it's hard to see how it would make gravitational waves. Awesome comment there. I'm not necessarily saying that dark matter might make the gravitational waves, although it might. We also have to consider, I made the comment, so I'm just going to tease some more things here, that the best place to study the fundamental nature of dark matter is the early universe. And if you'll remember the last guest I had on this show, the topic of conversation was primordial gravitational waves in the very, very first few seconds of the universe. So those are fun topics to think about. I'm just putting it out here. Okay, that is the big question. It is indeed. It is very much the big question. At least I think so. I think it's a fun question to ask. I don't have the answer yet, but I think it's a fun question to ask. And of course, I'm not the only one asking this question. There are other people asking this question. It's a good point to finish the show on this week, though. So thank you everyone for coming. It's been great fun. As someone pointed out here, we've had a lot more questions than answers today, but this is good because this is the thing with dark matter. There are so many questions and so little answers, but we are doing our best to figure it out. And someday, maybe in the future, I will start a Cup of Cosmology stream with, hey people, we found dark matter. I will probably be jumping up and down, and as soon as the stream starts, you'll know based on my reaction. But someday, hopefully, I can do that. I'm not sure if I'll still be doing Cup of Cosmology streams by the time we figure out what dark matter is. I'm not sure if I'll still be around. But let's see. I'm optimistic that within my lifetime, I'll get to do the stream of, hey, we figured it out. Someday, maybe. Really great questions from everyone today. I loved all of the questions. It's really fun. We covered a lot of different aspects of dark matter. So thank you everyone for all of the great questions. Cup of Cosmology will be back next Sunday, same time as usual. That's 7 p.m. Central European Summer Time, 1 p.m. if you're on the East Coast in the US, 10 a.m. if you're on the West Coast in the US, and 8 p.m. if you're in Helsinki, where I am. So I will be back online next week. I'm not sure what topic we'll cover next week. We'll figure that out. And remember, in October, we're going to have a bunch of guests. But for now, this has been really great fun. I hope you will tune in again next week. And I hope in the meantime, you'll stay safe and take care of each other.